We're going to continue with Erik Berg. Erik Berg is a graduate of Uppsala, and he has been involved in industry, in accelerated and startup companies. Now he's a researcher at Ericsson, and he's focusing on performance evaluation mostly. So his talk is about energy-efficient parallel software for radio-based stations.
Okay, thank you. I think you can hear me. So I'm really happy to be here and see some of my old colleagues. I call the talk Energy Efficient Parallel Software for, thank you, for radio base stations. And if you look at the title, that's something wrong with the title. Energy and software doesn't really match. Of course, you need some hardware before you can consume an energy. But of course, that forces me to also fiddle a little bit with hardware. And so I end up in the sort of in between software and hardware, and it's actually quite fun to be there. Why energy performance? So first I'll start to talk about why we need to focus on energy performance. That's becoming increasingly important, as I will show you. And then I will talk a few words about an EU project we have in common with the university world. And then I'll go into a few words about workloads that we have at Ericsson. And then I will talk about how to collect data on real hardware. That is really important to us in this project. And I will finalize with some concluding remarks. So why energy performance? Well, it depends on how you talk to. If you talk to some economic guy at an operator, they will say, oh, okay, we consume too much electricity, that's bad. But you could sort of also end up talking to the entire society, and of course you want to save energy to create a better world. So it's not really just all about building more power plants, though that would be way more cool if you're an engineer. I have these pictures showing a trend in radio access networks. If you look at the diagrams up here, upper left, you have a big base station, essentially, consuming energy in the kilowatt range. You can break that energy down into different parts. So on top you have the red one. It's sort of main supply. You waste some energy there. You also have cooling and stuff if you have that kind of a base station. You have DC converters. And then of course you have a baseband processing stuff. Here's the blue part in a base station, doing a lot of computations, and you see some of the energy actually goes there. Then of course you have more radio frequency stuff, and the big blue part there is the power amplifier. So in a big base station, that one is really the big power consumer. If instead you look into the future, you will find tiny base stations, tiny cells. Okay, we still have most of the power consuming parts, not the cooling, because you get rid of fans and stuff. You can't have them in a tiny base station just for covering a room or two. But of course, the power amplifier power goes down, but you still have this box. You have to do the computation, all the baseband processing and protocol stack and so on. And there, if you go there, the computation will actually consume a very large fraction of the total energy. Looking at the current network situation, I have brought two pictures. So the one to the left shows data collected from major city somewhere in Europe. They are sorted according to how much they are used, so average load. So from left you have the ones that you hardly ever use, and to the right you have the most loaded base stations. And then you can see, looking at the colors, to see sort of how much they are actually utilized. And if you look at that, you will figure out that, okay, even the most loaded base stations, they are really mostly idling. And if you go to a base station in a rural area, they're almost always idling. Still, they do consume power. I work quite a lot with different architecture groups at Ericsson, trying to figure out how to match the architecture and the computer and match it to the software. So you can look at the problem like this. The problem we're trying to address with this Adept project. So you have a piece of software. We're lucky at Ericsson because we know what software we run. It's not that piece of code we run, it's millions of lines of code. And you have some kind of hardware, and it's a multi-core system usually, a big one. This is sort of in the 100-core range, actually. And you can have, of course, you can have a lot of mismatches there. Maybe you have a code that consumes way too much cache memory, much more than you have in your machine. Okay, you will lose a lot of performance there and waste energy. Sort of, you have to get data from memory that you don't have to get otherwise if you had a well-dimensioned cache. But on the other hand, you can have a too big cache and then just waste a lot of energy having a cache that you don't use. So it can go both ways. Looking from the software perspective, you can of course have other problems. You can design your code in a way that really doesn't match the hardware. So you can also try to adjust the software to match the actual hardware you have. That's also a way to go. And once you sort of get these two to smoothly working together, I would say that we have a power efficient software running on that hardware. So what do we do about it? We want to learn more about it and figure out how to understand when this will be a good match. I am currently working quite a lot into a project together with university. It's an EU founded project. We're working with these guys. It's EPCC, it's a parallel computing center in Edinburgh. It's us, Ericsson, of course. We have Ghent University. They're really good at computer architecture. It's Professor Lieven Eckhout. And we have my old home university, Uppsala. And there we have a great computer architecture group. And then we also have involved Alpha Data. They do FPGA stuff just to make it more heterogeneous. The first point here, enable real or at least realistic workloads. I completely agree with the previous speaker before lunch. Pitfall number 5, I think it was. You have to run the real benchmarks. Otherwise, you can't dimension your system correctly. And at Ericsson, we're quite lucky because we write the application ourselves. But still, you have to be able to collect performance data on the real system. You can't just pick a tiny part of the application and run that and try to collect some data in a slow simulator and believe, okay, this is going to be representative for my entire system. It's not going to work. You're going to make mistakes in your system design. If you're going to make statistics, you have to make representative sampling. That's important. And you also have to sort of capture the most important bottlenecks. Say that your system is limited by memory performance. Of course, you have to be able to capture parameters that actually tells you something about memory behavior. And it could be interconnects, and it could be actually the kernel or the core in the CPU that's limiting performance. And once you have all that, you can also have expect to have a reasonable accuracy. But I mean, okay, if you go 20% off when you try to understand part of your system, it's not that bad compared to picking the completely wrong benchmark, because then you're way off. And I also think if you try to evaluate a system, I mean, your toolbox should be easy to use. Otherwise, no one would ever use it. This is one view of a system that you could run in this box. You have different layers of software in the protocol stack. You have very different characteristic of the concurrency you have available if you're going multi-core. On layer 3 type protocol stacks, that part you have quite a lot of task concurrency. You get signal input, you update some state, and then you signal something out. On the lower layers, say the signal processing, usually in layer 1, you have quite a lot of data processing, and it's data parallel. So this is just an example of what it could look like on layer 3. You have a state machine in the black box in the middle. E and B stands really sort of base station. And you talk to some user equipment, a phone somewhere, and you send a lot of signals back and forth, and you have to update a state in the base station, essentially. And there you go, you have task parallels. If you go signal processing, you'll have data parallelism instead. These workloads are usually of the kind that, okay, you get data input in one end, you do some processing, you forward a chunk of data and move on and do some processing, and then forward the data again. You can often describe these workloads using graph-like structures. And you get quite a lot of data parallel workloads. So you can split the data in data chunks and go parallel. And you can often get good efficiency even if you parallel over lots of cores. Oh, now getting back to where I started once upon a time. Someone figured out the reuse distance was a great thing to measure. Say that you have a core that is executing some kind of program. And you have a timeline. And you're executing loads and stores. And these touch different parts of the memory, denoted in this table here, A, B, C, D, E, and so on. You can actually start to collect data about how long time it takes for a program to first touch a piece of data and then touch it again. In this example, you had a number of loads and stores there. You have something reading or writing, F, and then you do something in between, and then you go back and read or write F again. And then you have a pretty short reuse distance, just 2. I mean, often you have millions of other memory accesses in between. This is, however, very useful if you want to model cache behavior. And it's easy to collect runtime in a realistic application without excessive slowdown. And if you use this, you can actually estimate miss ratios of arbitrary caches. That would be the collected data to the left. As a histogram, you collect, okay, how many times do I access data after just one access, after 2, 3, 4, and so on. You get sort of a fingerprint of the application's behavior. And then to the right, you have miss ratio on the y-axis and cache size on the x-axis. And then you quickly get an idea of how big should I, how big cache should I have in my system. We're working on that one, actually, on ARM, to start sampling on boxes like this. And the goal is to sample on real applications that we have at Ericsson to actually understand the behavior. And when you go on in this project, we will, of course, attach this to many other different models so we get a complete picture of the system, not just the memory system. When you sample on real hardware, it's really essential to have low overhead. Otherwise, you can't fulfill this requirement that you want to run realistic workloads, and then you're way off because you're running the wrong benchmark. And of course, it has to be representative and so on. And further on, if you want to have a complete picture of the box, you need many other kinds of statistics before you can create a model. That's sort of a really quick introduction to modeling performance that we're doing. If we would try to apply this, I think it would be most interesting, obviously, to look at it on the small cells, because computation is such a big part of the total power consumption. So if we look at this small femtocell here with capacity to cover a room or something like this, you could actually end up looking something like this. Suppose you have, to the left here, you have a sea of DSPs doing signal processing on the layer 1 stuff, and you have perhaps packet processing on the upper layers. Maybe you start out something like this. The red ones are running hot. The blue ones on the bottom are really idling because you dimension your system to have some kind of overhead or headroom. Sorry. Then of course, if you know about your system, you can optimize it and then just cut away some of that energy that that box is consuming, though this box would be smaller in a small cell, of course. But still, even if in a tiny cell like this, just picking the very right sizes of everything and make it work together, you could perhaps gain 20% of the computation, and that would make 10% of the total. Now, I showed you this picture. This is both good and bad news because your system is probably mostly idling anyway. It's not running hot. Maybe run like this at 10% load. DSPs usually don't scale as well as packet processing. The signal processing usually has to sort of keep running anyway because you have to listen to the antenna and decode any signal in case a phone comes into the room. When it comes to packet processing, you can turn off even more. And of course, in that case, you would gain even more, especially if the radio unit is very, the output of the system is very low. So you can think of the x-axis here as some kind of utilization of the base station. If you have a lot of active users, you have to output a lot of power. If you're mostly idling, you don't have to output that much power. You can go idling quite a lot. And then you, of course, can gain way more, save way more energy. So just to conclude this talk, it's really important to run the real workloads because we're not going to make this if we don't run the real workloads. And accuracy should still be good enough. Something we wish for the future is really that we would learn more about how to turn things off when we're not using them. That is something that we should dig more into in the future and do more research on, because if you have a workstation-like system, it's quite easy to turn off stuff. If you have a more real-time system like this, it's not that easy to figure out when and why you can turn things off, because you have to be ready to handle an incoming signal at any moment. That's a reason why systems like this tend to keep running full speed even if you don't have to. So that's a wish for the future that we will learn more about. I think I'm actually running out of time, so thank you, and thanks to my co-workers.
Thank you. Any questions? No. So,
No?
just yeah.
It's okay. You mentioned the importance of using real workloads,
Yes.
or at least realistic ones.
Yes.
Which are the set of benchmarks that you're starting with, or what kind of programs you're looking at, especially when you're testing your code before deployment? So what are the real workloads that you're testing with?
Okay, so I mean, right now in the research phase, we're really just using smaller examples. But I mean, in the future, we intend to develop a system so we can sample and collect data on the real workloads to have a setup with a sort of product and sample data, and that is what I would call a realistic workload. That's a goal, sort of.
Thanks. So it seems that you're one of the things you're looking at is memory performance.
Yes.
As cache performance. Are there caches in this silvery little box, or are you planning to put caches in the silvery little box later?
Tricky questions. There are actually caches at many levels. Yes, there are. Some of them are more special purpose than others, but yes, there are caches for some of the parts. Yes, I could say this is a very heterogeneous system. So we've fallen directly into one of the pitfalls there to create a really complicated system. But if you want to do something that is actually really optimized for, say, energy and performance and so on, you end up using every trick in the book. So DSPs, ASICs, general purpose processors. And the general purpose processors, of course, have caches.
Hey, when you said about the sampling what is ongoing, so sampling the hardware, are you thinking to have a kind of statistics sampling in the real time and gather such a type of information also for understanding the evolution on time of the traffic?
Let's see if I understand you correctly. Yes. You mean you could have
sampling means a lot of things.
Yeah.
Could be sampling because you are sampling the usage of the memory in order to optimize, for example, the cache entry, so decrease the TLB miss, for example, or you are sampling the resource usage in the system, so to optimize the resource usage in a way that you can follow the
I would say we're sort of primarily sampling sort of properties of the system. Say, I showed you an example here. It's the reuse distance. It's how sort of often you reuse a memory position. That's a kind of data we'd like to sample. You can also sample, I mean, instruction frequencies and so on. That's the kind of data we want to have to understand the overall system performance. But then, of course, if you have an efficient system, you can have this up and running and apply different workloads. Say that you have no user phones using the system and a lot of phones, and you can have different characteristica for different usages of the system.
Okay, thank you. Let's thank the speaker again.